speaker, Professor Michael Allen from Physics Department, Riordan University. Yeah, so he will talk under the title Riordan Arrays.
Okay, thank you very much for inviting me. Riordan arrays are something I found out about fairly recently. I have to thank my collaborator Ken for introducing them to me. We have a collaboration to do with tiling, and we came up with this number triangle, and we found that there's some relation with this number triangle to these things called Riordan arrays. So I thought I ought to learn a bit about them, and the best way to learn something about them is to give a seminar on them. So I found it a little tough going. If you look up Riordan arrays on Wikipedia, you get a definition which is actually not the current definition, which didn't help. There's 2 seminars on YouTube. I found the one by Zeleke quite helpful.
He's my brother.
And the paper I found most helpful was this 1994 one by Sprucanoli. Also, the Zeleke's talk was heavily based on a sort of lecture note type article called A Survey of Riordan Group by Shapiro, who was the originator of the Riordan Group. So in the talk today, I'll tell you what a Riordan array is and talk about some of the simplest properties. We already know we already are very familiar with one example of a Riordan array, which is Pascal's triangle. Then I'll look at the brief history of Riordan arrays. They've been around since around 1990. I'll briefly mention the Riordan group. I just out of interest, there's a group structure to these arrays. I won't use that later. And then we'll go on to some theorems which you can actually use to prove various things. The first is the partial sum theorem, which allows you to prove lots of identities involving sums. And then we'll look at another way of defining Riordan arrays, and also another theorem to do with them, which allows you to calculate things to do with paths on lattices. So first of all, what do we mean by a Riordan array? Well, it's to do with, we have two functions of x, which we can think of as generating functions, in the sense that they're power series. The important thing is that the first one has a constant term, the second one, q, doesn't have a constant term. And the Riordan array itself is a matrix with these entries. So the nkth entry, where both n and k start from 0 for convenience, is given by the coefficient of x to the n of p times q to the k. So it seems a bit of an arbitrary thing to define, but it turns out to be quite a useful thing, a useful tool. So as I've said, this notation we'll use a lot today. Square brackets x to the n, anything to the right of it. So all of this means the coefficient of x in the power series of all of this. So what can we get so far from this definition? Well, if you think about it, the first term in the series for p times q to the k, if we imagine multiplying this by this, this to the power k will give us q1 to the k, x to the k, and we're going to get p0 multiplied that. So the first term of that is going to be that. So if we're going to extract the coefficient of x to the n from this, if k is larger than n, we'll get nothing, because all the other terms are going to be higher order than that. So that's basically why we end up with a lower triangular matrix. All the terms above the diagonal will be 0. Also, it's fairly easy to see that the leading diagonal will just be when k equals n, and then we'll just get p0 q1 to the n as that term. And the first column is just when this is the 0th column, k equals 0, putting k equals 0, then we just get entries, and we just get P0, P1, P2 going downwards for the first column. So the first column is the generating function, or the coefficients of the generating function for P of x, and the kth column is the generating function, well, it's the coefficients of the power series for P times Q to the k. So effectively, you've got a matrix. The first column is just P, then you've got P times Q squared. So it's sort of like a geometric series of generating functions. Now, these Riordan arrays, as far as I know, only have applications really in combinatorics. And for that reason, P and Q tend to have integer coefficients. So in principle, they could have any real number coefficients. So a very familiar example is Pascal's triangle. It turns out if I put P equals 1 over 1 minus x and Q equals x over 1 minus x, I get Pascal's triangle if I follow that rule. And we'll just see how that works. So recall that in Pascal's triangle, the binomial coefficient n choose k is the nkth entry. So for example, this is row 0, row 1, row 2. This is the n's, this is the k. So row 2 choose 1, for example, is 2. So let's just see how that works. So by the way, my notation, which some people use, is to actually say this thing here, PQ, is the Riordan array itself. This is a matrix, and this is the nkth element of that matrix. So according to the definition, the nkth element of this Riordan array is the quotient of x to the n of p times, this is p, times q to the k. So we do a bit of manipulation with that. The 1 minus x, we can multiply with the 1 minus x to the k to give us this. And this x to the k would come out the front. Now, hopefully it's fairly obvious that we can change this x of n times x to the k to just x to the n minus k. And then we just have to deal with the rest. We just expand this using the binomial theorem. But actually, all we want is the coefficient of x to the n minus k out of all of this. So we just look at that coefficient here, and multiplying top and bottom by k factorial, we see indeed that it is n choose k, as we expect. So the Riordan arrays weren't actually discovered by Riordan. They were just named in honor of them. So this guy, Lou Shapiro, wrote a paper on them, submitted in 1989, and decided to name them after a famous combinatorist, John. I'm calling them Riordan. Actually, if you look at the YouTube seminar by Shapiro, he calls them Riordan arrays, but I've got used to calling them Riordan, so I might call them Riordan sometimes. They're actually generalizations of something called renewal arrays, which were introduced by Rogers in 1978 as themselves generalizations of Pascal's triangle and similar sorts of triangles. So Rogers actually came up with some theorems which now apply to Riordan arrays. Spugnoli is another important influence, pointed out the connection between these arrays and combinatorial sums in a very useful paper in 1994. These two other people have joined Paul Barry, now publishes a lot of papers. If you look at Journal of Interesting Sequences, there's quite often a paper by him mentioning Riordan arrays. He's also written a primer on Riordan arrays. So the Riordan group I'll just mention briefly. So it's a particular set, infinite set of Riordan arrays, such that the P0 is always 1 and the Q1 is not allowed to be 0. So if it's a group, then we have to have a method to compose a group operation on the elements. So the elements of the group are the matrices, the arrays, little p, little q, and big P, big Q. It turns out that, fortunately, the group operation actually corresponds to matrix multiplication, ordinary matrix multiplication of these arrays. But we can actually formulate it in a different way, which is more convenient than actually multiplying out matrices, which is the following. So it's p times little p times big P operating on q, little q, and then the new Q of the composition is big Q operating on little q. Okay, so if it's a group, we need 4 properties, which are the group should have an identity element. The identity element is 1x. This is fairly easy to see. If we multiply little p, little q by 1 and x, what do we get? Well, the function 1 just returns 1 all the time, so we just get p times 1, we get p again. And if big Q is x, then this is just the identity function, so we just get little q again. In terms of matrices, if we think about what the Riordan array is corresponding to 1x, well, it's the nkth component of, this is p, this is q. So p times q to the k is simply 1 times x to the k, and the x to the n component of x to the k is just the Kronecker delta, delta nk, which is the identity matrix as you expect. The inverse turns out to be defined in this way. You can check it by plugging in stuff. So where q to the minus 1 just means the inverse of q, in the sense that q of q to the minus 1 is x. And of course this just corresponds to the inverse of the matrix. And finally, well, not quite finally, associative we can probably check using this, or the fact that it corresponds to matrix multiplication. Matrix multiplication is associative. Another important property is that it's closed, and that's the one we really need to check. It's fairly easy to see that it's closed. We need that this element here, we've said that p naught has to be 1. So is the constant term of this new p here, is that equal to 1? Hopefully that's fairly clear that it will be. P itself has 1 here, and then we're multiplying that by big P of q. Now big P itself must have a constant term of 1, so therefore this thing overall has a constant term of 1, and this one should have